Good day, everybody. This is just for a test. Can you hear me well? Okay. Thank you, guys. We're going to wait 2 minutes and then we start. So, good day, everybody, and welcome to this web conference where we are going to speak about blast simulation and realistic 4D blast simulation. Before we start the subject, I will briefly introduce myself, Thierry Bernard. I've got a Master of Science in Physics and Mechanics and a PhD in rock and explosive behavior. I started my career 30 years ago as a blasting engineer, and then quickly started to develop the technology for the blasting industry. Some people say I was a pioneer in electronic detonators, developing the very first stage of electronic detonators in the years 90s. And I did that for basically 18 years. And in years 2003, I sold the technology to a BME group in South Africa. And then I started this new venture that is blast simulation. And since 2007, I'm managing the DNA Blast group. This is a group of company specialized in blasting engineering and blast simulation. And we've got operation basically all over the world. And with us tonight, we've got Alan Diaz-Butron, that is our manager of South America. We've got Ricardo Fernandez, that is manager of Bolivia, Luis Adrian Bernal in Mexico, Irina from Russia. Alan will be my assistant, and Irina too for the questions. So feel free to use the chat during this conference and ask some questions or put some comments. And Alan will collect the comments for the Spanish guys and Irina for the Russian people. and myself, I will deal with the English one. And at the end of the conference, we will answer some questions. So this is the topic, and I'm going to wait just 1 minute. I can see lots of people being signing in. We just wait 1 minute, and then we start the conference. Okay, so I think we're going to start. So the purpose today is a model for realistic 4D blast simulation, and this is a story that started a long time ago. It started basically in years 1936 with the Turing machine. The Turing machine was the first mechanical computer. It was a computer, but the first machine be able to duplicate a process and compute some information with nuts and bolts, and it's the very beginning of the computer science. Quickly, 10 years after, you've got the ENIAC computer, one of the first computers, huge computers, few tons, to run basic calculations. And very quickly, but 30 years after, we had the beginning of the computer, personal computer, with the Apple II, a very famous computer. And IBM followed the trends with the first IBM PC in 1981. From that, we had the ability to develop software, and one of the very first software, what was called Multiplan in 1983, that was the ancestor of the Excel spreadsheet, was the very kind of software that give us the opportunity to program some formula and do some basic simulations very easily. A big event in 1990 was the first graphic cards that allowed us to have, of course, nice display on the screen, but also to start fast calculation. And in the years 2000s, the calculation with the graphic cards was so fast that you can have some very nice 3D model like this, mechanical 3D model where you can calculate all the stresses that you can have in a car during a running stage. And this was due to the power of the graphic cards. Thanks to that, now we're in 2020, and this computer power have increased so much that we have the ability to do some 4D blast simulation. What is 4D? It's a 3D plus time. Here on the picture here, you can see the video. Here you will have the bench of a query, and here you've got the model one. So what you see here is not a photo, it's definitively a model that is based by cloud of points, and here you see that the bench where the blast is has been modeled. And if I'm running the video, you will see on one side here you will see the blast movement, and here you see the simulation. Just to run it again, you can see that it's very similar, and this is what we call 4D simulation. This is the simulation in 3D versus time. If you look at the result, this is the final result with the actual mug pile, and the green one is the simulated mug pile. And if you look at it, the simulation is fairly accurate. And to give an idea, to have an idea of that, we are going to do a cross section. So you're going to see a cross section of the model here, and you see the predicted one and the actual one, and you can see that is really fitting well wherever it is in the mug pile. So this is what we're talking about 4D simulation. So the real challenge is to predict a blast result. And every miner, blasting engineers ask one day in his life, maybe every day, the question is, what is going to happen when I'm going to press the trigger? Is it going to do this? Nice, smooth blast with no fly rock, fairly homogeneous fragmentation, no backbreak, no fumes, and here we cannot see it, but certainly no vibrations. Or is it going to do something like this? A very unexpected blast with lots of fly rocks, fumes, and certainly vibration at the same time. So it's always a challenge to predict the result. There are various techniques to predict the result. The first one is the trial and error method. This one is based on experience, and basically on experience. And it's something that costs nothing, and it's just simple to use. But the negative is that the experience is very long to acquire. It could take years to have a good experience. Most of the time, experience is qualitative. There's no numbers in experience. It's just, I remember that this happened like this, I did that, and the result was this. So you don't know exactly what you can expect. There's plus or minus no recall. I say plus or minus because some people, they've got a very good memory and they can remember everything. And with the modern technology, we can have some records. You can have taken some notes in a book. You can have taken some photos, videos. So to a certain extent, you can build your experience with some records. The big issue is when your experience is on book like this, and like what I have got behind me, if I need to dig on these books, on these photos, on my hard drives to find the right configuration, it can take some time. There's basically no explanation of what is happening in experience. It's just a recall of facts. I have done that, and I noticed that the result was that, but there's no explanation behind. So this is the first way of doing that. And it could cost some time and some money if you do some trials and error, and you have to try many times before you find the result. And if sometime you do some bad experience, and it could cost you some money. But it's certainly one of the most used techniques to design a blast so far. The second one, and we have seen it with the spreadsheet when they happen in the 80s. The spreadsheet is a very nice way to program some formulas. It's easy. It's quantitative because in the spreadsheet you play with numbers, so you can have some value information about that. It's a low cost, does not cost a lot. The drawbacks of a spreadsheet is most of the time the calculation you can do on a spreadsheet are generic. What I want to say by generic is that you don't have really the ability to deal with a specific configuration. You're basically doing with global principle, like what are the vibration at X meters from a charge with a K and alpha factor, but it does not describe exactly the configuration. But it's good. It gives you some trends, but only trends. You can use a third technique that is very common today, is what I call 2D software with formulas. This software are quantitative, so they also play with numbers. They've got some graphics as an output, so it's nice. You can visualize graphically the informations. The negative is that it could be statistic based. Sometime and most of the time, this software they do some regression analysis on data. And statistic is like experience. It's only describe what you have experienced before. You can have some trends with the statistics, and the beauty of the computer is that they do it very well and quickly and with large numbers, so there's no problem. But it's only based on the numbers you put in. In another word, if you never face the configuration, you don't have any chance to predict it correctly. Most of the time, they model only one effect at a time. It's some simple formulas that describe one phenomena, such as maybe the PPV, but not the frequency, not the waveform itself, or the fragmentation, the mean size, but not the full distribution. And by nature, they don't copy nature's mechanism. If it's empirical formula, it's just a formula that describe a phenomena based on statistics. And they don't take into account all key parameters because they model only one effect at a time. So the approach that I want to share with you tonight is what we call realistic 4D blast simulation. So the name includes everything. It's 4D, so as I said, it's 3D. So you've got the environment in 3D with X, Y, Z. You've got the third dimension. This is the picture that you can see here. This is the modeling of a bench in 3D. It's realistic because it's really copy the nature mechanism. It's cover all the aspects of the mechanism. It's physics based. It really duplicates the real world. Here you can see that and the movement, one stage of the movement. And because it's based on physics, it can adapt to all or any configuration because the physics describe the real phenomena, so you don't need the experience to use it. And you've got result 3D plus time. There's big negative points on this one, is that you need accurate data. Of course, if you want to model the reality, you need to have good data that describe properly the configuration. It's not a big deal today. The technology allows us to do that, but there's a challenge to collect this data. So now, what we can say is that to a certain extent, simulation, it's like a crystal ball. It's something that gives you the ability to see the future. If you can predict the result, if you can see the outcome of your blast before you press the trigger, you see what is going to happen tomorrow. And this is something where you're going to be very comfortable if you press the trigger and you know that your blast is going to happen like this. So now let's look at the model and the structure of the model. We're going to see what is inside and how we can organize the information for that. How to model a blast? the question is there a single equation like this very famous equation, E equals mc2? That is an equation that describes the universe. Einstein explained us that from this equation you can derive everything, and you can model the universe with that. Okay, that's fine. Now we're talking of our blast operation. Is there a single equation for this kind of things? As far as I know, not really so far. This is involving thermodynamics, ballistics, mechanics, fracture mechanics. So we don't have one unique equation that we can apply for that. So we need to find another way to approach this phenomena and to model the phenomena. The other way, I'm going to describe it now, is to look at what we need to do such a model. First, you need some geometry. The geometry is associated to the rock mass. The rock mass has an external surface, and the surface is the geometry of your blast, of your area. And so the surface is only the top, and the rock mass is what is underneath the surface. Then a key player in the process is, of course, the explosive that play a large role because the explosive is the energy source for the mechanism. And then we've got the time. As I said, it's versus time. Initially, it's 40, 3 plus 1. And when you look at a blast, it's something that is short, 1 second, half a second for a quarry blast, sometimes a few seconds, 3, 4 for underground blast. Anyway, it's a very short event, but it doesn't mean the time does not occurs or happen in the mechanism. From the time you press the trigger to the time the rock lies on the ground fragmenting, many mechanisms happens. And this is versus time. That's why we've got the time involved in the process. And in the center of that, we've got the physics. The physics is complex. It's not. We don't have one equation, sorry, for all these phenomena. As I said, we've got the explosives that produce gases. So this is some thermodynamics principle. Then you've got some fracture mechanics where the P waves in the rock, they create fractures. Then you've got the expansion of gases. And then you've got some ballistics for the fragments. So there's lots of physics principle involved. And for that, we need to find a way to deal with these 5 elements. The idea is very simple. As we cannot model accurately the whole mechanism, what we're going to do, we're going to discretize everything. And why discretizing everything is because we want to go up to a point where we've got simple objects, very simple objects, where in between the object, you've got simple interaction. And if the objects are so simple, we can have an equation to describe it, sometimes a simple equations, easy to model, and same thing for the interaction. In another one, I just want to solve some equation like this, 1 plus 1, and I don't want to solve very complex equations. So let's start with the process. We're going to discretize the rock mass. Discretizing the rock mass is at the same time the geometry and the rock mass itself. And for that, we're going to create what we call a voxel model. What is a voxel model? It's a model based of elementary cubes. A voxel is basically a 3D pixel. A pixel is a square box in your screen, and a voxel is a box in 3D. And we're going to create a 3D model that is a sum of these elementary cubes that we call voxel. And we're going to model all the geometry and the rock mass. Each of these voxel will contain geological data, fragmentation, or concentration, and some other data. And here you've got a view of a bench, and this is the view of the bench in 3D. And when it's model, the rock mass here with the voxel, you've got this model. So you can see you've got lots of voxel piles together to obtain the same geometry that you've got here. Explosive. This is the second part of the equation. We're going to discretize the explosive in sphere. This is a borehole with, for example, two types of explosive, bottom booster and a detonator. And what we're going to do is modelize, discretize this borehole with some spheres that are piled together like this. Each of these spheres will contain some explosive data, diameter of the borehole, and basically timing. And we're going to do that because we've got very good equation for the explosion of a sphere of explosive materials, and we can have a discretization in the vertical axis, but also versus time. Keep in mind that the time here will be the initiation time that you've got here, plus the detonation time, the velocity of detonation that progressed through the sphere. The time itself, very easy to discretize with a time increment, a time step. And the idea is to do some calculation every time step. And this calculation we're going to see in the next slide. Now we're going to discretize the physics. So this is an interesting part of the model. The discretization we're going to call genes, and a genes is basically it's an elementary mechanism. Like here we have selected a few. Like the first one is detonation that will provide, we'll see the pressure, fragmentation, ejection velocity, free phase, ballistics, and shock. Let's start with the detonation gene. This one is going to take as input parameters the explosive specification and basically the borehole diameter to produce a pressure field. So the output will be the pressure, and keep in mind we've got the time behind, we've got time increment, time step, so it's going to be pressure versus time. Detonation pressure. Here you've got a cross section, for example, of a bench. You got the borehole here with the sphere, and this is the voxel. And if you look at one of these spheres here, when it's time for the sphere to go off, you will have a calculation of the pressure inside, and this gene will calculate the pressure in each of these spheres. Then you've got a fragmentation gene. This one is able to calculate the number of cracks that will be produced in a voxel. As an input parameters, you've got the pressure field, you get the pressure that is going to apply here on this voxel, the rock features, and of course the location of the voxel. The output will be the number of cracks. Once again, I come back with the cross section, and if I'm look at this voxel here, this voxel versus this sphere, here you will have a P wave and a S wave traveling from the sphere to the voxel, and you will have then a reflected wave coming back. And here in the voxel, you will have the effect of these incoming waves and reflective waves. Both will be create some cracks inside. And you will have a number of cracks in the voxel. Now we're going to move to the ejection velocity. Ejection velocity is something that will calculate how fast a voxel is going to move and in what direction. For that, if you, once again, we take this voxel as an example, and versus this sphere, you've got a contribution of the sphere to the movement of the voxel in that direction. And if you take a second sphere like this, you've got a contribution in that direction. So it means for this voxel, the contribution of these two spheres will be a velocity like this in this direction. You can imagine the process that you repeat the process for each sphere for all the voxel, or for all the voxel for all the sphere. So for each voxel at the end of the process, you will have an ejection velocity. The next one is the free phase gene. This one is going to describe how the broken free phase is going to evolve versus time. If you come back to the example of the cross section here, where we've got the spheres and the voxel, at one stage, some voxels here have some fragment inside, and you've got enough energy to move. So when they start moving, you've got a boundary that change, and here you've got this boundary, this limit that is in between the intact voxel and the previous one that has been fragmented and have enough energy to move. This is what we call a dynamic free phase, and this dynamic free phase will be the next free phase for the next borehole that is here at this stage. And then we've got finally the ballistic gene. This one is the one that is describing the movement. So now for each of the voxel, we've got an ejection velocity, and these voxel are going to fly following a very standard Newton law. And the very last one is the shock gene. We've got voxel flying, and they've got interaction. They shock each other. So when two voxel like this, they've got interaction. If we zoom on the interaction, you will see they interact together. So you've got some repulsion forces that apply in between the voxel that will move the voxel in a new direction. And the next step will be that for the voxel at the next step increment. Finally, we've got the time step that cover everything. And if we link all these genes together, starting from detonation that create the fragmentation that is generating some movement and ejection speed that is creating a virtual free phase. And then from this virtual free phase, you've got the ballistic that push the gen out and they shock together. And everything is versus time. So you compute the process gene by gene up to the end, and each step increment, you start again the process. At the end of the day, you will have this result. This is a pile of voxel that will describe the final result. So we have covered the mechanism. We have seen how we can discretize a complex mechanism to produce a model that will duplicate the reality. Now I will show you some example where we run this model in real case, and you can see how it's performing and what we can do with that. So that is the next step. The first example, we're going to see a detailed example in an iron mine, for example. Okay, where we're going to look at the dilution, and we're going to see at the ore grade location in the muck pile. Oh, this is a top view of a blast, very standard top view. You can see the blast, different colors of the holes for different loading. This is the 3D view of the design. And if you put the design with the terrain surface that you have it here. So I have highlighted the first row here. So you can see here you get the first row, normal first row, and here you've got also normal first row. Here we've got some material in front of the first row. So the burden is very thick. This is the geological data. This is the ore grade. I think blue is the low grade and red is the high grade. And this is the voxel creation. So here, as I explained before, we have converted the terrain surface and the rock mass into a voxel model where each voxel contains the mechanical characteristic plus the ore grade. And this is really duplicating the real surface of the terrain. And you can see the bench here. This is at the end of the first calculation, and we have here color-coded the voxel with the fragmentation. So the red color means you've got some fine fragmentation inside, and the green one is a coarse fragmentation. Here you've got a very light green because it's a buffer blast, and the mud pile that was in front has not been fragmented by the blast. It was already fragmented. And this is the initial velocity calculation result. So what you can see is that where you've got all in front of the free face, you've got a high ejection velocity. Here too. Here you basically have no ejection velocity because it's buffered and you've got the mud pile in front. Here is the ballistic shock calculation. We're going to look at the video, and you see the movement with the associated dilution, and you see the movement in 3D. Few times. So what is 3D versus time? So you see exactly where the rock are flying, how they fly, and where they go. And you also see the dilution process. So you see the mix of the different colors that is due to the movement of the rock. This is what we've got with a 3D plus time. If you look at the cross section, for example, of the mud pile, we've got a fairly good matching. So you can see that the top surface matches quite well the mud pile shape. This is another example. This is a quarry simulation where you've got here the quarry blast, and here we've got the model. So in this model, everything is taken into account except the footholds. Here you've got 3 footholds here that was not taken into account in the model. And if you look at how the rock flies and the movement of the mud pile, and if you look at here, it's very similar. model is you don't have the dust, so you have a better view of what is happening. And at the same time, you've got the fragmentation distribution that is calculated, and each voxel containing its own fragmentation. Yeah, I can see some message that say that you've got some audio issues. I will maybe try to speak slower, and I'm gonna pause the webinar. I'm gonna relaunch it. Okay, maybe the audio will be better now. Is it better for the audio now? Okay, it seems it's not better. Anyway, I can't not do anything, so I will. There is too much interference right now. I will try to go slower. Yes, the presentation will be is saved, and you can review it later on. Okay, so I continue with the query simulation results. Once again, you've got fairly good matches with the simulation and the real mug pile, the actual mug pile. The trends are very, very good here for that. This is another example. This is we can do the same thing in tunnel, in underground. Here you've got the tunnel, and you will see this is the voxel model, and you will have a view of the blast. I think it's not very often that you can see a blast in tunnel from that location, and you can really see what is happening inside and the movement. If you rewind the blast and you play it again. And one thing we can do also with the 3D modeling is cross-section. And here you can have a look of your underground blast in a cross-section and really see the process, fragmentation and movement process, and see how things develops. And even here at the back, you see the remaining part that is not blasted. You can see the back breaks. You can see a lot in the model. The next one is another example in underground. It's huge blast in underground, ring blasting, with where holes are drilled from the top cavity, and you've got from top gallery, sorry, and you've got a cavity underneath. And this type of model, there's only the cross section that can help to understand what is happening. So here you're going to see the detonation happening in the middle. And the flow of the rock that go into the cavity, and this is ring by ring, and then you will have the next rings coming up with a faster time, and you will see the rock flowing down into the cavity. So that really gives you the ability to see what is happening inside. And in this kind of blast where there's no possibility to have a visual view of the detonation in the real world, we have the ability to see what is happening. I have seen some question about the tunnel modeling only with electronic detonators. No, you can do it. You can do the modeling with any kind of detonator. Here, just come back to this 3D modeling, and here you've got a cross section, and if you see the cross section here, you will see we're going to rewind it, start from the beginning, and on the other right you see how the rock flows in the cavity. And the last example I've got here is about the vibration result. This kind of model allows us to model everything, including the vibration. If I'm running the model here, you've got a quarry here, and all the quarry has been modeled in 3D here. And you will see there's a blast in the middle, and you will see the vibration radiating around the blast. And when we zoom in, we see the movement of the blast. So at the same time, you've got the movement of the blast and the vibration. And here we're going to rewind it. And replay it again. So you can really see at the same time all the process, movement, fragmentation, and seismic data. A few words about calculation time, because when we do such calculation, we can imagine it takes a lot of time, and it's true. And just give you an example, and the first mine blast we have seen, there's about 200,000 voxel, 7,000 charges, that is individual charge sphere, and about 2,000 time steps. So if you look at the number of calculation we are doing, it's about 1,000 billion calculations. So it's a lot. If we do a standard computation on a CPU, we can consider it's going to take a day to do that. And the current model is running parallel computing. If you use parallel computing, and especially on both CPU and GPU, it's going to be 15 minutes. So 15 minutes is something that is very reasonable according to the kind of result we've got today. And of course, with the increasing of the power of the computer, what is 15 minutes today is going to be 5 minutes tomorrow and 1 minute the day after tomorrow. Let's come to the conclusion before we go to the questions. As a conclusion, we can say now that we've got a realistic 4D simulation available. All these models, you can run it, and they're running it every day. You've got various use for that. Dilution, that's what you see here in the conclusion. Mud pile shape, if you do cast blasting, and you're interested in the shape of your mud pile for digging, overbreak, fragmentation, or vibration simulation. And the simulation time is very compatible with the production time. So Now you can run a model and do multiple test cases on your computer. If it takes 15 minutes in a day, you can do 4, 5, maybe more combination of parameters and test these parameters and see what are the best. So this is to conclude the presentation. First, I would like to thank you for all of you that you attend to this presentation. I have seen there's lots of questions, and so I will answer to some of your questions. I've got a recap of the question by Alan, and I'm be glad to answer to these questions. So I've got some questions about yes, about is it only possible to do this simulation with electronic detonator? Okay, the answer is yes and no. The good thing with electronic detonator is you've got an accurate timing, so it's an accurate data for the model, but it doesn't prevent you to use non-electric detonators, and the model will deal with that. So there's no problem with doing the simulation with a pyrotechnic detonator. I've got questions about the correlation between the reality, the actual data, and the model, especially on the fragmentation or the vibration. One thing that I haven't mentioned is that there's a calibration process in the model. A calibration process means you run a first model, you take the actual data, and you look at from parameters for having the best match between the model and the actual. And once the model is calibrated, the results are fairly accurate, whether it's fragmentation, vibration, or movement. I've got also some questions about what we use for creating the voxel, what kind of data we use. We use basically cloud of points, mesh cloud of points. So the mesh cloud of points, they come from any package that you can have. You can use 3D laser scanners, you can use drones, whatever, to produce a mesh cloud of points, and we can import it and start the voxel from that. I've got questions about size of the voxel and size of the sphere of the discretization. So the sphere is very easy. It's always the diameter of the borehole, very simple. The voxel themselves, you can select the size you want. And just keep in mind that when you divide the size by 2, you've got a more accurate result, but you increase the computation time by 8 because it's a function of the power of 3 of the size of the voxel. But the voxel size, it's whatever you want. You have to give some thinking about the geology, like if you've got some joints with 1 meter spacing, maybe the good size for the voxel is 1 meter. But on the principle, whatever the size you want, you can use it. This is one of the key questions I have seen. There's much more questions on that. What we're gonna do is we're gonna put this web conference. We're gonna give you a link to access to the video later on, so you can review it, and I guess with a better sound. We can also send your questions to one of our guys here. If you can see the email address, you can capture it. You can see your question. Can send your question directly to one of us, and we will be very happy to answer to your questions. Okay, guys, thank you once again for your time, and I wish you an excellent day and excellent weekend. Bye bye, everybody.